The fourth talk of 5 in the session is on parameter-free sentence embedding via orthonormal basis.
All right, hello everyone. I'm Ziyi from Stanford University. So today I will talk about the parameter-free sentence embedding model by leveraging orthogonal basis. So in general, the sentence embedding model can be categorized into two classes. The first, the paradigmized models. For example, you train a sentence encoder by using the neural network, but usually this model is not computationally efficient. For example, you usually need GPUs and also you need large-scale amount of training data. So in contrast, the non-parameterized model, for instance, we try to represent the sentences as a weighted sum of the raw vectors. So you can usually run the train or the inference on a single CPU. So this is highly desired and needed in some computational resources scarce cases, for instance, when you run the mobile devices. And also, usually you don't need large-scale training data because in some cases you don't have any trainable parameters at all. But however, in the previous work of non-parameterized models, the performance of these models are not comparable with these parameterized counterparts. So our goal here is to learn a non-parameterized models that it also has competitive performance compared with the parameters counterparts. So our model is actually inspired by this question: what is a sentence in mathematical sense? Let's see an example. So when we say this sentence, a man is dancing, we actually is spanning a subspace of a sentence that is spanned by its word vectors. So what's happening when we form this subspace? So first, the word A comes. It also brings in a new orthogonal basis to this originally empty subspace. And then the second word, man, enters the subspace. So we can decompose the vector man into two parts. The first part that is parallel with the vector A, meaning we can represent this part with the original Q1 orthogonal basis vector. And there's another part that is perpendicular to the Q1 that we can compute by subtracting the projections of vector A, subtracting the projection of vector man onto the Q1. So what's left is the new orthogonal basis vector Q2 that the vector man brings in to this new subspace. I know like on the 2D this not look like perfectly perpendicular, but since I need to plot it on 2D, then yeah, you got the idea. So we can do the same thing for the vector is. Basically, the vector is brings in a new orthogonal basis vector Q3 that is perpendicular or orthogonal to both Q1 and Q2. So this Q3 is the new semantic meaning or the new semantic direction that brought in by the vector is. And then the same thing for dancing. So dancing also brings a new orthogonal direction Q4. So the takeaway here is the sentence is actually a subspace spanned by its own word vectors. And each word, when it enters this subspace to form this sentence, it might bring in a new direction or a new semantic meaning, Qi. So the above process is also known as the Gram-Schmidt process, which is an algorithm to compute a set of basis vectors in the subspace. And this Gram-Schmidt process can be conveniently rewritten in a matrix factorization form. So say we write a matrix S, while each column, well, the ith column of the S is the ith word vector of the sentence. Then we can run the QR factorization. Well, each column of the Q is a orthogonal basis vector, and we just compute it. And R is the ith column. R is an arbor triangular matrix, and ith column of R is the projections of ith word vectors onto the orthogonal basis vectors in the columns of Q. Okay, then since the Gram-Schmidt process only processes the words that comes before the word comes before WI. We also want to include the information that comes after the WI. So what we do here is if we want to quantify the new semantic meaning Qi for the WI, then we define a context window of WI, which includes both the n preceding and n following words of WI. And then we run the QR factorization on this. And then we shift the WI to the last column of its context window. Then we obtain a new context window matrix Si. Then we run the QR factorization on this Si. Then the last column of the Q is the new semantic meaning that's brought in by the WI with respect to its context window. So also we have the projections of WI onto the orthogonal basis vector we just computed. Okay. After we compute the new semantic meaning QI of a word brings in, we want to measure the importance of a word from 3 levels. So in a single word level, is WI brings in enough novel information, and also in WI's context, the novel information brought in by the WI is important. And also in the corpus level, the QI, is it QI unique enough to be expressive? Okay, the first level, in a single word WI is QI dominant. We believe that if the WI, if QI, the new semantic meaning, is dominant in a word, then this word should be more important. Therefore, we compute therefore define the first weight, the word-wise weight alpha W, which is to be the exponential of the proportion of QI in WI. So, for example, here, since we have the projections of the QI onto of W on the QI, and basically this is the projections, the proportion is the projection divided by the norm of other the projections vector. And also the second question is, in the information, all the information WI's in WI's context, is QI important? So here we want to know if QI is important in SI. The first thing we need to know is to decide which semantic meaning or directions are important in SI in this context window subspace. So there's a very natural to do this linear algebra, which is single value decomposition. What I mean here is we run the single value decomposition on the side, and then we can get a new set of orthogonal bases, which is stored in the columns of UI. And also we get a singular diagonal, which is sigma I, while the diagonal of the sigma I is the singular values. So each which singular vector in UI has associated singular value stored in the diagonal of sigma I. So we regard this singular values as important scores of the singular vector. All right, so we run the SVD on that side, and we then obtain a new basis vector. Then what we do next is to compute the QI's projections onto this new orthogonal basis vector. And then we weight each projections by multiplying them with the corresponding singular value. For example, here, if the QI's projections onto the singular vector is 0.1, then we times the 0.1 with the first singular value of SI, which is a corresponding single value with the first single vector. And then we'll do the same for the second and the third projection and so on. So we define the second weight, the contextual-wise weight alpha C, which is the norm of the weighted projections divided by the context window length. So the last question we want to ask is, in a sentence corpus, is the new semantic meaning QI unique enough? Just like the idea of inverse document frequency, if a word that is too common, then it is very likely that this information brought in is not important enough. So we want to find the common directions or common semantic meaning in this corpus. If the QI has a large alignment with these common directions in the corpus, then WI should be assigned with lower weight scores. So the mind map is given a sentence corpus composing of n sentences from S1, S2 to Sn, we want to decide which directions are common in this corpus. So the answer is the same. We used SVD. But we need some pre-process calculations. So we first need to encode each sentence SK into a coarse embedding CK. So say we write the SK into a matrix form, that the ith column in SK is the row vector of ith word in SK. And then we run the SVD on the SK, and the coarse embedding of the sentence K is computed as the singular vectors times the cubic of the single values. So the cubic function is decided on the STS benchmark development dataset, which I will talk about in detail later. Okay, after we encode each sentence into embedding matrix, now we have a corpus matrix X, Well, the ice column of X is a coarse embedding of the I sentence. Then we compute the top singular vectors from this X. Then these M singular vectors are regarded as the common directions in this corpus. And then for each sentence SK, we rank this M singular vectors by the alignment with the sentence matrix weighted by the corresponding singular vectors. And then we select the top R common directions. And finally, the corpus-wise weight alpha p is defined as exponential of the negative projections of Qi onto these common directions. The reason why we use exponential of negative is because if we want that, if the alignment is bigger, then the alpha I should have a smaller corpus-wise weight alpha p. Okay, in summary, we propose a parameter-free sentence embedding model called geometric embedding because we utilize the geometric structures in a sentence subspace. So first, for a word Wi, I want to find the new semantic meaning Qi brought in by this Wi. We define a context window, and then we run Q factorization. Then we can. The last column is the new semantic meaning by this brought in by this Qi, and then we measure the importance of Wi from three aspects. So first, in a singular word level, is Qi dominant enough? On the context level, is Qi important enough? On the sentence corpus level, is Qi unique enough? So finally, the sentence embedding model, the sentence embedding is the weighted sum of the word vectors, and the weight is the combination of these three-level weights. Finally, the experiment parts. So the first task we do is a sentence similarity task that runs on the STS benchmark dataset. So this dataset is composed of sentence pairs, and each sentence pair is given as a cumulative score. So in order to validate a sentence embedding model, we compute the similarity score of the sentence pair generated by from the vector generated by the sentence model. And the evaluation matrix is the Pearson-R correlation between the cumulative score and the cosine similarity score decided by a model. So as you can see, our model, like highlighted in GEM, produce comparative results even compared with parameterized models, and also compared with the ISF, which is the smooth inverse frequency model, probably the previously best known parameterized sentence embedding model named simple but tough to beat baseline, would beat this simple baseline by significant margins. And also the second part of experiments is on supervised tasks. So these datasets are standard NLP and NLI datasets. What we do here is, so for example, the SST. So given a sentence of a movie review, we want to classify this movie review into either positive or negative class. So what we do here is we generate a sentence embedding for this sentence, and then fix the sentence embedding, and then we train the neural structures for these downstream tasks. So our model achieves the best state of art in the non-parameterized models. Also beats the tough to beat by significant margins, and also it shows really competitive results even compared with those highly parameterized with even billion parameters counterparts. So in summary, we propose a geometric embedding model for sentence embeddings, and we identify the new semantic meaning of a word brings in by applying the QR factorization. And then we measure the sentence embedding, the importance of word from three levels. Okay, this is what I need to talk about today. I'm happy to take questions now.
Okay, let's thank the speaker. We have time for questions.
So did you do anything to look at, for example, which of the three weights that you're computing to get your overall weight has the biggest contribution? Like, I might have thought, like, if I were just starting this from scratch, I might have tried one of them and then be like, oh, that's good enough. And so, like, how did you end up with these three specifically?
So basically, this is a mind map of adding a blocks after one weight after each weight. So I would say like the first two weights are playing probably the more important parts.
Other question? So I could ask, there's a few parameters in the model that got broader context, including the sliding window, but also there's the corpus on which you're computing some of the metrics. Was it quite sensitive to these parameter choices, or is it a pretty robust method in general?
I would say if you like, for example, if the M top vectors, if that falls in a reasonable range, which is like a range of 10 number, then it doesn't play much difference. It make much difference. But we like find the best hyperparameters on the development set of STS benchmark dataset.
Okay, let's thank the speaker.